We want to calculate the moment of inertia of a rod, uniform rod, length 30.5 centimeters, mass 60 grams, as it's rotated about a point through one end of the rod. To set up an integral to do this, we consider a small mass or small length increment delta x at some position, where x star is the distance from the axis to some point within that delta x interval. The moment of inertia of the mass within this interval is just mr squared, where m is the mass. We're going to call that delta m. Okay, so let's take delta m first. Let's figure out what the mass of this of the rod within this increment is, and that's very simple. We just have a simple proportionality. This is delta x over L of the whole thing. So we multiply delta x over L times m, and we get the mass within this small interval. Okay, it follows then that the contribution to the total moment of inertia for this interval is delta m times the square of the distance of this interval from the axis, and that distance is represented by x star, so it's delta m times x star squared. And I got a little note here, r equals x star. If you think of moment of inertia as a sum of all the mr squareds, then r is the distance of a point from the axis, and in this case that distance is x star. So the sum of all the delta i's is going to be the sum of all the delta x star squareds delta m, and the delta m is m delta x over L. I've rearranged that to put the x star squared in the middle. This is the order in which we want these terms when we take the limit to get our integral, just because everything looks better that way. No compelling reason to do that. Factoring out the m over L, which is constant from the sum, we end up with the sum of x star squared delta x. And that sum is going to approach, and I have an equal sign where there I should have an arrow. So this is going to approach m over L times the integral of x squared dx. And the limits on the x stars are 0 to L. So that the limits in the integral will be from 0 to L. So we have m over L times the integral from 0 to L of x squared dx, and it's very easy to do that integral. You get 1/3 ml squared. Now, I've glossed over a lot of the details that you need to go through to make this a little more rigorous. Okay, we probably want to put subscripts on these intervals and have a sum from I equal to 1 to n of x sub I squared delta m, and so forth. In physics, we kind of do that, but I've got feet in both worlds, and actually probably more in the mathematical world, so it makes me a little uncomfortable to do that. But this gives you the idea. You've been through a calculus course, so I expect you know how to fill in those details. Be sure that you do, because if you can't do that when you really need it to verify something, you can get yourself in trouble. It's okay. So anyhow, we got 1/3 ml squared for the moment of inertia of this rod. Then I'll note, as I've noted before, the relationship between this and the moment of inertia that we get if we rotate the rod around the center. Talked about that previously. If we were rotating about the center, then on the average, these x stars would be half as great. So we would be integrating, well, our masses on the average would be twice as close to the axis, which means our mx squareds or mr squareds, whichever you want to look at, our mr squareds or mx squareds would be on the average 1/4 as great, because we'd be squaring the r's, which are on the average half as great. Now, there's more to that argument, and I'm not going to go into the details now, but we've talked about it already. Okay? A question came up. Where would a point mass have to be point mass of 60 grams have to be to have the same moment of inertia? Well, you can do that rather easily. You just let x be the distance at which you put your total mass m, and you set mx squared, which would be the moment of inertia of a point mass at distance x from the axis of rotation, equal to your 1/3 ml squared, and solve for x. And I believe the solution is rather straightforward. We divide both sides by m, and then take the square root of both sides. We'd have the square root of 1/3 times L. And the square root of 1/3 is better expressed as square root of 3/3. So that's square root of 3/3 times L. So if we concentrated all of this mass at that distance, and square root of 3/3 is kind of close to 0.6, okay? It's 1.732 divided by 3. If it was 1.8 divided by 3, it would be 0.6 of the length. So it's a little over halfway, not quite 60% of the way from here to this end. Concentrate all the mass there, keep some kind of a massless connection here, and you'd have the same moment of inertia.